everybody, welcome back to part 2 of this week's lesson, where we're going to be talking about predicting products. In order to be successful, you will need the predicting products notes, which are found on the same sheet as the balancing equations notes, a writing utensil, your chemistry notebook, and most importantly, a periodic table. Please make sure you have that. Pause this video if you need to get one before moving on. Our objectives for today's lesson will be to predict products of a chemical equation using just reactants. In order to be successful, the most important thing that you need to know how to do is how to write chemical formulas of ionic and covalent compounds. If you can't do that, then you will not be able to be successful in these other 3 criteria, and you will not be able to predict products. So we can sum up predicting products based off 3 important rules. The first step that you always need to do is to identify the type of the chemical reaction that's occurring. This can either be a synthesis, decomposition, single replacement, double replacement, or combustion reaction. Once you've discovered what the type of reaction is, you can determine what your product should be. If you are forming a compound, it's most likely going to be ionic, so you need to make sure that you do your cross and drop to find your new ionic formula. Only after you have discovered your products and have written them in the chemical equation can you begin to balance. And once your equation is balanced, then you are finished. I've broken down the types of reactions based off the reactants only. I do want to note that we are only dealing with like simple cases. We're not going to make it super complex, so please don't freak out. In terms of predicting products, if you see 2 single elements by themselves for reactants, then it is a synthesis reaction and it will form 1 compound. If you see 1 compound by itself as a reactant, and that's it, that's just 1 thing, then it will form a decomposition reaction, meaning that it will produce 2 single elements, or polyatomic ions. A single replacement reaction involves 1 single element and 1 compound. The single element actually replaces the cation or anion in the compound, and so it forms 1 new single element and 1 new compound. If there are 2 compounds for the reactants, that means that this is a double replacement reaction. And if it's a double replacement reaction, it will form 2 new compounds. The cations will just switch places and recombine. And finally, the last reaction is a combustion reaction. This one is very specific because it deals with a hydrocarbon and pure oxygen gas. Remember that a hydrocarbon can be identified as either a combination of just pure carbon and hydrogen, or it can be a combination of pure carbon, hydrogen, and oxygen. But either way, if it's not one of these 2 and it's not mixed with pure oxygen, it will not be a combustion reaction. But if it is, then it's really easy because the products will always be CO2 and H2O, carbon dioxide and water. And it's easy because you don't even have to worry about like doing cross and drop or anything. It's just automatically CO2 and H2O, and you can jump straight into balancing. So let's look at some examples of a synthesis reaction. Remember that a synthesis reaction has 2 single elements combining to form 1 compound. In the first example, I have aluminum and nitrogen. Before I go any further, I'm going to write out these elements with their charges. So I have aluminum 3+ and nitrogen gas, which is 3-. Once I've written that out, then I can do my cross and drop to find my compound. And when I do that, I end up with Al3 and 3. The 3's actually cancel out. So our final product would be AlN. And once I've got that, I can balance my equation. You should be familiar with balancing, having watched part 1 of this week's lesson, so I'm going to rush through this a little quickly. If I have aluminum and nitrogen on both sides, I have 1 aluminum and 2 nitrogens on this side, and 1 aluminum and 1 nitrogen. I need them to balance out, and nitrogen's not balanced, so I'm going to add a 2 coefficient, because remember, you can never add or change subscripts. It has to be coefficients. So I'm going to add a coefficient, which gives me 2 aluminums and 2 nitrogens. Well, now my nitrogens are balanced, but not aluminum. So I'm actually going to go in and I'm going to add a 2 coefficient for aluminum. When I do that, that changes to a 2, and now aluminum is balanced and nitrogen is balanced. Another way that we can do synthesis reactions is by actually writing it out. If I have sodium and chlorine, when I combine them to form a compound, it's going to form sodium chloride. So I can write that out. After I've written it out, then I can go back in and replace it with formulas. So sodium, single element, it's just Na, and chlorine is one of your diatomics. Remember, Brinkelhoff or Hoberfinkel, have no fear of ice cold berries. So what that means is it's always going to have a 2 coefficient, or sorry, a 2 subscript. And now I'm going to form my compound. When you form your compound for sodium chloride, once again, you need to do your cross and drop. Do not just combine them. You actually need to do the cross and drop every time. So plus, minus, and you end up with NaCl. Once I've done that, then I can go back in and balance it. So I'm going to put a 2 here and a 2 here, and now it's balanced. Let's take a look at another type of reaction known as decomposition reactions. If synthesis reactions involve 2 single elements combining to form 1 compound, decomposition does the opposite. It takes 1 compound and breaks it apart into 2 separate elements. So in this example, I have Al2O3. A lot of people make the mistake of just bringing everything, including the subscripts, across and writing it out like this because they think, oh, that would combine to Al2O3. This is the number 1 mistake people make. Do not transfer subscripts. This is incorrect. I'm going to show you guys the correct way to do decomposition reactions. It always breaks apart into 2 single elements. So what I'm going to do is I'm just going to look at the elements, and I can see that it's aluminum and oxygen. So I'm going to write out aluminum and oxygen. Now the only other thing I need to do is ask myself, are there diatomic molecules? Aluminum is not diatomic, so we're good. But oxygen is. That means that I just need to put a 2 subscript here, and then I'm done. Well, not quite. Now I need to go back in and I just need to balance it. So I'm going to set up my atom counting on both sides. I have 2 aluminums on the left and 3 oxygens, and I have 1 aluminum on the right and 2 oxygens. So I'm going to add coefficients. Where to start? If you watched the part 1 video for balancing equations, then you remember that when we're dealing with the 3 and a 2, we have to look for a number that they both have in common, which is 6. So I'm going to turn both of these into 6 by adding the corresponding coefficients. I'm going to add a 3 coefficient here to get 6 on the right, and I'm going to add a 2 coefficient on the left to get 6. So now I need to update my aluminum count as well, and I have 4 aluminums now on the left. That means that I can put a 4 coefficient here, and it balances out. This is the least common because it doesn't have any common denominators. So we're good. I'm going to do another example where I'm dealing with dinitrogen monoxide. That means that dinitrogen, that's 2, monoxide is 1, so N2O. If I were to break this apart, once again, the first step I'm going to do is just write out the single elements. So I'm going to write out N and O. Once I've done that, my next step is just to see if there are any diatomics. And it just so happens that both of these are diatomics. Brinkelhoff, Oberfinkel. Nitrogen and oxygen are both diatomics, which means they both require 2 subscript. It has absolutely nothing to do with this 2 subscript on the left. So now I'm going to go in and I am going to balance my equation. I have 2 nitrogens on the left, 1 oxygen, and I have 2 nitrogens on the right and 2 oxygens. So I can add a 2 here. That turns into 2 and 4, and I can add a 2 there. So now it's balanced. Let's take a look at single replacement reactions now. A single replacement reaction deals with a single element replacing another element in a compound. So if that single element happens to be a cation, aka has a positive charge, then the cations would switch places. And if the single element is an anion, aka a negative charge, then the anions will switch places. I said cation instead of metal on purpose because hydrogen is a cation, so hydrogen would switch places with a metal. Let's take a look at this first example. I have zinc and hydrogen monochloride. So if I were to figure out what's switching places, I know that zinc has a positive charge. Doesn't even matter what charge, I just know it's positive because zinc is a metal. Hydrogen is also positive, so these are both cations. So that means that zinc is going to switch places with hydrogen. Before I do anything else, I'm just going to write that out and say that zinc is now going to bond with chlorine. In cases like this, on practice problems where you're doing it on your own, I would give you the charge of zinc just in case, because it is a transition metal, so we don't know its official charge. I am going to tell you that zinc has a 2+ charge, and chlorine, you should know, has a -1 charge. So when I do the cross and drop, I get 2 and 1. So the first compound that's going to form is ZnCl2. And now hydrogen has been replaced by the zinc, and so it's on its own. Go back, ask yourself, is hydrogen, the single element, a diatomic? Hydrogen is, so I'm going to put a 2 subscript. We only need that 2 subscript if it's diatomic. Otherwise, it can exist by itself. So now that I've formed my products, I'm going to go in, and once again, I'm going to balance, and I'm going to do the balancing just a little bit quicker. I'm going to clear this up a little bit so you can see. I'm going to put 2 over here. That gives me 2 and 2, and oh, look, it's balanced. I'm going to do another problem. If I have lithium bromide and fluorine, I don't even need to write them out yet. I can if I want to. I know that lithium is a positive charge because it's to the left of the staircase. It's a metal. Bromide is bromine, and that is an anion. It's a negative charge. Fluorine, which is the element by itself, is also a negative charge. It's to the right of that staircase. That means that bromine and fluorine are going to be the ones to switch places. So now instead of lithium bromide, you're going to end up with lithium fluoride. And once I've found that out, I can write it out. So if I have lithium bromide, that is LiBr, do your cross and drop, plus fluorine. Fluorine is diatomic, Brinkelhoff. It's the F in Brinkelhoff. So I add a 2 subscript. Remember, I only add the 2 subscript if it's diatomic. and it forms lithium fluoride. Once again, cross and drop, lithium has a +1 charge, fluorine has a -1 charge, so I get LiF. And once I've done that, I go back in and balance. If I have 2 fluorines on the left, I need 2 on the right. That means I also need 2 here, and I knew I forgot something. Bromide is the single element here. And so it is part of Brinkelhoff, and there's 2. And I need, that's good. So make sure I didn't have room over here, but make sure that you would also put bromine. Oh, I do have room. I can write on that. Very cool. Okay. Here's a double replacement reaction. This one is always going to deal with the cross and drop no matter what. Always do your cross and drop first before doing anything else. In this case, I'm also going to draw attention to the fact that NO3 is a polyatomic ion. And this is important because if you're dealing with polyatomic ions, you treat it just like a single element. It does not change. So what's going to happen in double replacement reactions are the 2 cations, in this case strontium and silver, are basically going to switch places. So our 2 products now are going to be strontium and nitrate, and silver, always put the cation in front, and chlorine. It doesn't matter which order you put them in, if you wanted to put silver and chlorine first or strontium and nitrate first. I do need to go back in and do my cross and drops. So looking at a polyatomic chart, you can see nitrate has a -1 charge, strontium has a 2+ charge, silver, we can work backwards and see that it has a +1 charge because nitrate has a -1 charge. So +1, and chlorine is -1. So once again, I'm going to do my cross and drops. So my first compound is going to be SrNO3, 2, and my second compound is going to be AgCl. Last but not least, do not forget to balance it. Keep nitrates together. If you have 1 nitrate on the left and 2 nitrates on the right, then we can add a 2 here. And we end up with 2 nitrates. We also have 2 silver now, so I'm going to put a 2 coefficient in front here. I have 2 silver and 2 chlorines, and everything is balanced out. Once again, I can write things out first if I want to. I can see chromium and zinc, and I know that these would switch places. So I know my new compound formed would be chromium 3. I am abbreviating it a little due to space. Chromium 3 chloride and zinc 2 nitrate. And once again, I can write out this equation itself after I've done that. If I have chromium 3 nitrate, that's CrNO3, 3 subscript at the end, plus ZnCl2. Once again, chromium and zinc switch places. So I end up with chromium 3 chloride plus zinc 2 nitrate. Now the last thing is to balance these out. Once again, pause this video, try to balance it on your own. When you've got it, hit play. So I'm going to go through and I'm going to balance these. I'm going to put a 2 in front here and a 3 here. Now I have 3 zinc, so I need to put a 3 coefficient in front here. And I have 6 chlorine, so I need to put a 2 coefficient in front here, and everything's balanced. I'm sorry if it's a little hard to read. It's hard to write on the computer. The very last one is actually the easiest one though, and that's the combustion reactions. I just need to look at this and identify, oh, carbon, hydrogen, and oxygen plus pure O2, carbon and hydrogen, pure O2. Don't even have to think about it. My products are going to be CO2 and H2O, always. And I'm going to write that out for both of them. It requires very little thinking, but a whole lot of balancing. So here's a helpful suggestion. Whenever you're getting ready to balance a combustion reaction, go show. What that means is always start by balancing your carbon. After your carbon is balanced, go back in and balance the hydrogen. Only after the carbon and hydrogen are both balanced, go back in and balance your oxygen. And the reason we do that is because oxygen is a single element each time, and so it's the easiest to balance at the end. So if I were to balance this reaction, I'm going to set up my atom count. Trust me, you want to do the atom counts for combustion. So if I have 3 carbons, I have 8 hydrogens, because 7 plus 1, and I have 2 oxygens. And now I'm going to add 1 carbon, 2 hydrogens, and 3 oxygens. So I need to go back in. I'm going to go show. So I'm going to look at my carbon first. If I have 3 carbon on the left, then I need 3 carbon on the right. Each time I do this, I need to update my count. So now I have 7 oxygens, but everything else looks good. Well, now my carbon's balanced, so let's take a look at hydrogen. I have 8 hydrogen on the left and only 2 on the right. So I'm going to put a 4 coefficient here. When I do that, that changes it to 8. So now, and it also changes this to 4 plus 6. So this changes it to 10 oxygens on the right. So now my carbon is balanced, my hydrogen is balanced, and I can move on to my oxygen. If I have 10 oxygen on the right, then I'm going to add a 5 coefficient on the left, which will give me 10 as well. And now it's balanced. Go ahead and pause this video and try to balance this next one on your own. When you're ready, hit play. So let's go through and try to balance this on our own. I'll rush through it a little bit more. If I have 2 carbon on the left, I need 2 carbon on the right. I have 2 hydrogen on the left, and oh look, I have 2 hydrogen on the right. So this one is okay. However, I have 2 times 2, so I have 4 plus 1. That gives me 5 oxygen on the right. I can't have 5 oxygen because there's no way that I can get this to an odd number because my coefficients always have to be whole numbers. So I'm actually going to do a trick. I'm going to turn this into 2 oxygens, and when I do that, that means I need to add a 2 coefficient on the left, and this is going to change my 2 coefficients, into a 4 coefficient. And once I do that, then I can look at my oxygen count, and I've got 8 plus 2, that's 10. So once again, 5 O2s. So now I'm going to show you guys some cool demos where we're actually putting these chemical reactions, everything we've learned, to the test. And you're actually going to write out what these chemical reactions produce in the end.
Hey everybody, welcome back. We are going to do another chemistry demo, and it's going to be awesome. These are all things that you probably have in your kitchen. I'm actually not going to tell you what substances we're using until the end, because what I want you to focus on are the signs that you see taking place for a chemical reaction. So I have this unknown liquid right here, and I'm going to pour that in. I measured out about 1 cup of this, but I may have added a little bit more because I figured, you know, if we get a bigger explosion, the better. I mean, we're in quarantine. What's the worst that can happen, right? So I'm going to go ahead and pour this in. This is just a flower vase that I may or may not have stolen from a parent a while back. And I'm going to scoop out some of this white powdery substance. I'm not going to tell you what it is, but you'll see that it's going to react with my liquid here. So what I'm going to do is I'm pouring it in using this bag, because then I'm going to, as soon as it begins to react, I'm going to, whoa! Okay, it's all over the place. So, what did you notice? I was originally going to put the bag over the vase so that you could see the reaction taking place. But hopefully what you can still notice is that there are bubbles all throughout the liquid. It is bubbling. And so we can see that gas is being produced. Already, because of this one thing, we know that this is a sign of a chemical reaction. So what ended up happening is I added baking soda and acetic acid, sodium bicarbonate, acetic acid, aka baking soda and vinegar. And when we combined those two things, a double replacement reaction occurred. And it happened so quickly I didn't even have time to cover it with this bag to try to trap the carbon dioxide gas that was being produced. One of the byproducts was also water, H2O. It's really cool to see and do. It's a lot of fun. Just make sure that you guys maybe do it over a sink. Well, I'm signing off, but remember, stay safe, wash your hands, and keep on practicing chemistry. I miss you guys so much. Bye.
So that was the first reaction. This is what I'm doing in quarantine. By the way, fun fact, I was actually on CNN a couple of weeks ago, and this was the experiment that they showed. And so I was so fearful that you guys were going to see this on CNN and think that I didn't do that with you, but I was waiting and I was going to show it to you this week. So yeah, this whole thing. So what I'm going to do is, this is a little bit more complicated. So I'm going to balance and predict this product for you. This is a double replacement reaction because we are dealing with, we are dealing with two compounds here. So when I predict my products, I'm actually going to get sodium acetate. And I'm going to get carbonic acid, H2CO3. And so what ends up happening is, as soon as this is created, this carbonic acid ends up undergoing a decomposition reaction. So then, and that's what causes that huge immediate like bubble up and explosion. So this carbonic acid, H2CO3, very, very quickly becomes H2O and CO2. And if we look, everything is already balanced, so we don't need to go back in and add any coefficients, but if it weren't, we could do that as well. The next reaction that you're about to see is a video reaction that was actually taken by you guys in October. So here we go. So one of my favorite things when watching that video is hearing all of your comments, because I definitely did not hear them during the experiment itself. But we're going to walk through this equation together. I have sodium plus water. So I added that sodium metal to a beaker full of water. This was during Halloween, by the way. I'm going to give you a helpful hint. Remember a few weeks ago, I told you that when we're dealing with chemical reactions, usually we write water as hydrogen hydroxide instead And that makes it easier to predict the products. So you should notice that this is a single replacement reaction because we have a single element, sodium, and water, which is a compound, hydrogen hydroxide. Sodium is a cation, which means that it's going to change places with hydrogen, but it's only going to trade places with that one hydrogen, not with the hydroxide ion itself. So the sodium and the hydrogen are going to switch places. So now we're going to end up with sodium and hydroxide and then hydrogen gas on its own. Sodium hydroxide, once again, you need to predict your product. So you're going to figure out the charges. Hydroxide is a polyatomic ion. You're going to do your cross and drop. So you should end up with NaOH plus hydrogen gas. Remember Brinkelhoff, so it's going to be H2. After you've done this, you can go back in and balance your equation. For instance, we have 3 hydrogens on the right and only 2 on the left. This one I'm not going to give to you, okay? This is something that you're going to balance on your own and then submit, and I will be checking for accuracy.
Hey everyone! Today I'm going to be making elephant toothpaste because elephants need clean teeth too, right? Well, okay. It's not actually what they use to brush their teeth, but it does end up looking like toothpaste, which is pretty cool. To get started, I'm going to need the following materials. I will need 3% hydrogen peroxide, a package of dry activated yeast. It's not a package, but it's the same amount. Dish soap, and food coloring. Since I don't have glassware from the lab, I'm actually going to do this experiment in a 2-liter soda bottle. Hopefully it works out. Better start drinking. So, if you can't laugh at yourself, then life's no fun. So, it's okay, it works out anyway since I need to put on my lab coat and my goggles. Well, that's easy. In case you haven't noticed, I've converted my kitchen into my own Hogwarts potion classroom. So I'm just going to go ahead and change. Okay, so now that I have my protective lab equipment, such as my safety goggles and my lab coat, which incidentally goes to show you should always wear them because if I had these on earlier, I wouldn't have had soda explode all over me. But now that I've gotten ready, I do want to give you a little bit of background before I officially begin. The only thing that's actually reacting in this experiment is the hydrogen peroxide itself. And this I just got from CVS. The yeast, which is an organism, contains enzymes. And so these enzymes act as a catalyst. So to begin this experiment, I'm going to start by adding approximately 1 teaspoon of yeast into my container, which has been rinsed out from the soda. If you have a funnel, use the funnel. And I'm going to add 2 teaspoons of warm water. If you remember from biology, when we're dealing with enzymes, which yeast is an organism that contains enzymes, we need to activate those enzymes. So warm water is going to allow us to activate the enzyme catalase found in yeast, which will lead to a really cool reaction. So I'm going to use about a 1/4 cup of hydrogen peroxide, and the thing about this hydrogen peroxide is, unfortunately, it's really weak. This is only a 3% solution, which means that we're not going to get as big of a reaction as we would if we were at school with more concentrated solution, but that's okay. So I have my hydrogen peroxide, and all I'm going to do is I'm going to add just a couple of squirts of dish soap in there, and just kind of give it a swirl so that they're all mixed together. So once I pour that in there, you can see that it's actually beginning to rise. And the enzymes from the yeast are breaking that hydrogen peroxide apart. So we'll see how big it actually gets. Unfortunately, it's not going to be that huge, big explosion that you sometimes see on YouTube videos, but that's okay. We're working with what we've got. So it looks like this is as big as this reaction is going to get. But what's happening is this hydrogen peroxide, when activated by yeast, is being broken down. And on your worksheet, go ahead and predict these two products, which I just told you. And don't forget to balance your equation when you're done. Bye.
So I'm going to let you finish predicting this product and balance that last equation on your own. Once you're finished, please upload your balancing equations notes as well as your predicting products notes onto Canvas, and then complete the predicting products and balancing worksheet. Remember that I'm here every day from 2 to 3 on Zoom if you need any help, and I can also do individual appointments around 1. Also, stop into Zoom to say hi. I miss you guys, and it's great to see you. I do have an optional extra credit this week that will replace your lowest assessment grade. It will only be available this week, so after April 29th, it will no longer be available. And everything else from T3, including everything for distance learning, has to be turned in if you would like credit for this. If you turn in the extra credit, however, you're missing work from previous weeks with distance learning, or you're missing work from before we left school, then you need to complete those before I will take this extra credit into account. As always, happy studying. Stay safe, stay healthy, wash your hands. I love you and I miss you all. Bye.